Thank you so much for that incredible introduction, Anirudh, and thank you so much for nominating me. And thank you all so much for being here. I'm really, really excited and honored to be here today, to be certainly to be receiving this award, which I'm incredibly grateful for, and also to be have the opportunity to share my work with you. Just a little bit of it, as Anirudh really called me out on. I have my finger in a lot of different pots, and I do a lot of different things. But today I'm specifically going to talk about how I work to harness the complexity of minerals to explore evolving Earth and planetary systems. So I'd like to start out by, let me see if I can use the clicker, by thanking several people. First of all, I would like to thank everyone who nominated me for this award. I don't actually know who they are. I know Anirudh submitted the nomination, and that's pretty much the extent of what I know. So if any of you are in this room, or if you're watching this, thank you so much. This really means the world to me to have received this award and to be with you all here today. I also wanted to take a moment, since this is for an award, I thought this was a moment that I could really say a few shout outs to some of the people in my life and my career that have really made a huge difference for me. I'd like to start out with my PhD advisor, Bob Downs from the University of Arizona. Bob is an incredible scientist and human. He taught me mineralogy and crystallography, but he also taught me how to be a scientist and how to do science, right? So he really, and that, I wasn't an easy student, so it was really a huge task for him to do, and I'm so incredibly grateful to him for the time that he has invested in me and continues to invest in me. We collaborate together to this day. I'd also like to call out Dave Blake. He is the PI of the Chemin instrument on the Curiosity Mars rover, and he took a chance on me and trusted me as a young master's student to come be a part of the mission and to actually run the Chemin instrument. I was the first one to break it, of course. Don't worry, it's fine. It worked out, but I did put it in safe mode. I was the first one to do it, and I will never forget. Dave is a wonderful human, and he's so gracious. And what he said to me when I broke this instrument on Mars, where we cannot go and fix it in any way, shape, or form, he said, you know, you only break things when you're doing something. And that was, how gracious was that for him to say that in that moment when I broke in his multi-million-dollar instrument on another planet. He's just an incredible guy, and he really, in that moment, instilled a lesson in me, don't be afraid to break stuff, right? And he really taught me that you're gonna break stuff, right? And you can't let it stop you. You fix it and you keep moving, and I'm so grateful to him for that lesson and much advocacy throughout my career. I'd also like to mention the rest of the Chemin team as well. An incredible group of scientists. Liz Rampey is one of them, Doug Ming, so many of them. But then I'd also like to mention Bob Hazen. He is the reason I came to Carnegie, and he's the reason I came to that fateful data science datathon that Anirudh mentioned. Bob is an incredible scientist, an incredible collaborator, an incredible mentor. He is so incredibly generous with his time, with his knowledge. I'm so grateful to him for teaching me to ask big, outrageous questions. Some of them you'll see here today. And for teaching me that I can take a non-traditional path in science and I can break out of the silos that I have been in. He also took me to that datathon. So he introduced me to Peter Fox, to Anirudh Prabhu, to Marshall Ma, to a group of data scientists who were incredible individual scientists in their own right, but also taught me the huge power of data science. And that first day of that datathon changed the entire trajectory of my career. So obviously there are a lot more people that I should be thanking, but I'll move on to give you guys some of the science. But I just want to say that none of the science that you're seeing here today would be possible without my data science colleagues and my very, very close daily collaboration with them to get this done. So, why did I get into data science in the first place? Mineralogy, in general, there are a few notable people who break away from this, is largely a descriptive science. We find things in the field, we create things in our lab, we measure them, and we describe them, and we report them. I got very frustrated with kind of the statistical toolkit that was available to me. Multidimensionality was not something that I had the tools or the skills to be able to handle. And data science has certainly changed that. And so in recent years, and I've been so happy to get to be a part of this, I have got to see my field, which was once very descriptive, move into a much more predictive space. So we're able to do things now like predict the number of missing mineral species. We're able to predict the location of previously unknown mineral deposits. We're able to detect biosignatures in networks of planetary minerals, and we're able to predict formational environments. So I promised several people that I was going to talk about what is my vision for the future of mineralogical sciences, but also earth and planetary sciences in general. And I'll say that that has three components. First is that it is data-driven. For decades, we have been developing these incredible data resources in mineralogy, but also outside of mineralogy. And now we have the data, and through machine learning and data science, we have the tools to be able to make these predictive methods to actually be able to answer some of these questions. It is also interdisciplinary. So we are crossing those silos. We are integrating with other fields, and we are answering questions that one field alone cannot. And it is multidimensional. A lot of you in this room have encountered these problems. A lot of geodata, in particular mineralogy, is very bad at this, geochemistry. It's very multidimensional. It's also small, sparse, and heterogeneous, right? And we need methods that can embrace this inherently messy and complex data. So why do I want to focus on minerals? Well, first of all, they're cool, which I hope everyone in this room can agree, and I hope you're all going on the field trip to the mine and we'll get to see some cool minerals. But that's a good enough reason in its own, but that's not the only reason. There are many. And the first I'd like to mention is that minerals are the oldest and most robust materials in our solar system. And they retain a record of what has happened to them, how they formed, and any subsequent weathering and alteration that they've undergone. So they're essentially time capsules. They enable us to go back in time and tell us something about the ancient history of our planet or of other planetary bodies in our solar system. Why data science? I don't think I need to convince anyone in this room, but it allows us to embrace that multidimensional, multivariate nature of these incredibly messy and complex and large systems. And it allows us to integrate across these different disciplines. Data science really can be the common language between fields and how we can actually come together to answer these questions together. So essentially, data science enables us to have a holistic view of Earth and planetary systems. So, what kind of questions am I asking? I said that I was asking some big ones, and there are many, but I subdued myself to only three for today. And the first one that I'm really interested in is, how do planets evolve through deep time, and what are the drivers behind their similarities and their differences? How can we deconvolve and characterize the complex feedback systems between Earth and life, both on our planet and potentially on other planets? And what are the mineralogical signs of life, and how can we detect them on other planets? So for my talk today, I thought what I would like to do is really give you a flavor of those many different projects, many different interests that I have. So I'm going to run through several different data-driven projects, and I'm going to highlight some of the main discoveries that were made in each one of these projects or subfields of my work. The first one I'd like to mention is mineral evolution. This is a field that was pioneered by Bob Hazen and has been around for well over a decade now, probably about 15 years. And essentially this relies on the premise that a planet's mineralizing environments are different at every stage of planetary evolution, from the time planetesimals are forming all the way in through modern day. And what this does is it provides us a temporal and a spatial framework for characterizing the physical, chemical, and biological conditions through deep time. So this provides us sort of a mineralogical lens, if you will. And that's really the way I think of my work, is Earth and planetary science questions with a mineralogical lens. So some of the, there have been a lot of discoveries with this, but some that I'd like to point out is that we have documented it with, in many cases, pulses of mineralization with supercontinent assembly. We've also been able to, there's a recent paper led by Dan Hummer, Oh, actually, it's showing right here. Here's a figure from it that shows Earth's atmospheric oxidation is recorded in those pulses of mineralization with supercontinent assembly. And we've also been able to actually quantify how long it takes for the Earth's upper crust to be oxidized with these, Earth's atmospheric oxidation. So that's a pretty cool discovery as well. We've also found a strong increase in mineralization with the rise of the biosphere. And I'll talk more about that in a moment. The next project I'd like to mention is pioneered by Greta Heisted, who is in the room right here. So I hope you'll ask her about this throughout this conference, and I know she's giving a presentation tomorrow. And essentially, this work relies on the fact that the diversity and distribution of minerals on Earth follows a distinct trend. This is an LNRE, or large number of rare events trend. Some of you are probably familiar with this, but in layman's terms, essentially what it means is that most minerals are rare and only a few minerals are very common. And what this allows us to do is borrow a technique from ecology. I believe someone mentioned the other day about the importance of seeing what other fields are doing and borrowing from their techniques. You know, they went ahead and they had all the pitfalls, so now we can learn from what they've done. So we really like to pay attention to what other fields are doing and borrow their techniques. So we're able to generate accumulation curves, and with this actually make predictions on the number of missing mineral species. This has led to a lot of new discoveries. The Carbon Mineral Challenge is a really notable one. If you're interested in checking that out, you can go to mineralchallenge.net. And between 2016 and 2019, over 30 carbon minerals were found after this work was put out and sort of the call was put out to the collector and the scientific community. Hey, we know that there are a lot of carbon minerals. Can you go find them? And over a 3-year period, they found over 30. So they certainly answered the call. The next I'd like to mention is really moving into a much more quantitative space, and that is mineral network analysis. So I said that the systems that we're working in are incredibly messy and complex. The data set that I brought to that initial datathon was over 700 minerals, and each one of those had 30 to 40 different attributes associated with them. I can't look at a spreadsheet and understand what's going on. I can't see the trends. So that is where we really started turning to network analysis, because networks incorporate and display many dimensions and attributes at once. They allow us to display complex data in a way that is digestible by the human brain. So we've been able to do visual and analytical exploration of these incredibly complex systems. And some of the findings, one of the things that are really cool about networks is often the findings really just pop out at you as soon as you look at the network. And that is true for many of the ones that I'm going to mention here today. First of all, we have found that there are embedded vectors. These are associated with age, chemistry, structural complexity. And these are embedded in networks that are just mineral co-occurrence. So you wouldn't necessarily expect to find this in these networks, but we do. And this is cool because, of course, we can recognize phenomena associated with these trends, but coming back to that sparse, small data problem, we can also use these trends to predict missing values and start to fill in our data sets that are a little bit holy. We've also been able to recognize historical punctuation events. What we're looking at here is the recognition of mass extinction events. And this specific technique led to the detection of a massive faunal turnover event in the trilobite record that was previously unknown. And again, this is, you make the network, you look at it, and boom, it really just pops out at you. So we like using this tool as an initial step in our data exploration. And basically what we're seeing here is major environmental shifts. We can also see this in minerals. Very recently, I've been working on some comparative planetology work. I've put together a database on Martian minerals, and I'm trying to compare how Mars's mineralogy relates to Earth's. How is it different? How is it similar? Why, right? Of course, underlying question is always why. We've also been able to recognize planetary scale biosignatures within mineral networks. This is something that I hope we're going to put out very soon. I'm really, really excited about being able to say, here is a mathematical, a graphical symbol of what a planet's mineralogy looks like if it had life, and what it looks like if it didn't have life. So we are very close to being able to put out a paper that actually says what that looks like. So moving on to the second project I'd like to talk about. And that is predicting Martian mineral composition. So as I mentioned, I work on the Mars Curiosity rover, but there is no spacecraft instrumentation that is capable of measuring the composition of a single mineral phase. And why do we care? I said it straight at the beginning of the talk. Minerals record the geologic and biologic history of a planet. So what are we on Mars to do? We are there to figure out the geologic and biologic history of a planet. So this is pretty important to doing that. However, we can measure bulk rock chemistry with some different techniques, but there is nothing that can measure the composition of an individual mineral phase. Of course, on Earth, we do this with a microprobe, right? But we don't have a microprobe on Mars. It's very hard to send an instrument that is, the size of a room and can't be shaken or get too cold or too hot to space, right? So what we've done is rely on the Chemin X-ray diffraction instrument combined with machine learning to be able to predict complex mineral compositions to the level and precision of a microprobe, which is pretty incredible. So we're employing a machine learning algorithm labeled distribution learning, and that predicts this multi-component, so major and minor element composition based on X-ray diffraction data alone, specifically the unit cell parameters. So where can we use this? Of course, we're using this with the Chemin instrument on Mars and Gale Crater right now. That has really helped us understand the geologic history of Gale Crater. People can also use this in Earth laboratories. If you don't have access to a microprobe, but maybe you do have a little powder XRD, you can use this. And this is actually, in my opinion, helping to democratize science for people who have these lower cost instruments, but not, $1 million microprobe, right? Or if you just don't feel like polishing it and taking it to the microprobe, this can be a first step for that as well. But what I'm really excited about is the power this has for future missions. So we were slated to be on a Venus mission, which was Venera D, and now due to political situations around the world, it looks like that's probably not going to be happening for us and any other US-based parts of the mission, unfortunately. But we hope to be able to send this instrument to other planets in our solar system, possibly the moon. And basically, we have upped the technology of XRD to that of sending now an XRD and a microprobe, which I'm really, really excited about, and it is a huge advance. I'd also like to mention mineral association analysis. So I hope that you all have had the opportunity to talk to Andrei, who has a poster on this subject. I'm the mineralogist, but he is the data scientist. So if you have questions about the algorithm and the method, how we actually did this, he is really the best person to talk to. So association analysis employs complex multi-correlations of mineral co-occurrence data to predict previously unknown mineral deposits and environments. So essentially, this is a recommender system that creates a probabilistic model that tells us what is the likelihood of finding the mineral that we're interested in. This is exactly what Amazon or Netflix or any of these online retailers and services do when they are making a recommendation for something that they think you might want to buy or watch. So it enables us to ask questions like, where can I find a new location for a mineral that I'm interested in? So this could be a mineral that has economic implications. This could be something that has scientific implications. Certain labs or study certain types of minerals for various reasons, and so they might want to figure out, hey, where can I find this? You also might just be a mineral collector, and you want to go find another locality of this. That could also be a fun use for this. You may also want to ask, where can I find a previously uncharacterized Mars analog site on Earth? Obviously I work on Mars, and I'm really interested in ways in which we can understand it better in any capacity. So there are places on Earth that really mimic those conditions that we have on Mars. And through this method, I can search a certain mineral assemblage and start to find out where those might be located. We're also able to determine a mineral inventory at a location of interest. So say you have a site that you've been studying and you want to think about what other minerals might occur there. This method can do that for you. So how does this look? We essentially generate association rules, and you can see what they look like here. So it's something like if calcite, pyrite, quartz, and sphalerite form together, how likely is it that you are going to find chalcopyrite there? So that is essentially what this method is doing. And then we have certain probability metrics there for evaluating that. We have put out a preliminary paper, the first step in a series of papers that are both improving the method, making it more robust and optimized so it stops crashing supercomputers, and also applying it to different places, different geologic settings, and different geologic questions. So one of the first questions that we asked in the paper was about this Mars analog site. So this is a site that was studied quite a bit for the Perseverance rover. So they did the Pixel instrument, if you're familiar with that. It's an XRF. They did a lot of the testing out in this area. So it's a Mars analog site, and we were interested to know what other minerals occur there that haven't already been detected. And we were able to generate this list and say, potentially these are minerals that we also might expect to find on Mars in addition to the ones that we already know to be at this analog site. The other type of query that we highlighted in this paper is where can we find a new deposit of critical minerals? We specifically focused on rare earth element minerals. I'm going to show you a monazite CE and lithium ore, so specifically spodumene. So with this method, we were able to predict several locations. You can see, what is that, about a dozen for each. And the really cool thing about this method is often you don't get immediate, especially if you're doing planetary stuff, you don't get immediate ground truthing of your predictions. But with this method, we did. It's very cool. So we were able to, we made this prediction just approximately 2 years ago, and in that 2 years' time, several of these minerals have been found at these locations. So you can see all that are highlighted in red and say yes, those are ones that have actually been ground truthed, which again, that's pretty exciting because I don't often get my results ground truthed. So we also better be right? If it's so easy to go out there and check, we better be right. I think we are. We did really, really well. So I'm very excited about this method and the future, which it's being applied to a lot of other different systems and problems. So the last project I'm going to mention has two parts, and that is the evolutionary system of mineralogy. And in my mind, this is really almost a culmination of a lot of the work that I've been doing, a lot of the thinking that I've had over these past, 10 plus years, we don't have to say how many plus, of my mineralogical career. And it basically relies on the fact that minerals are incredibly information rich. And if we can harness that complexity and harness all of that information, we can gain a holistic perspective of the dynamic materials and processes that formed our solar system, our planet, all the planetary bodies in our solar system through deep time. So the first question that we had to ask in this project was, what are the modes of mineralization across our solar system and through deep time? So what are all of the ways that minerals form throughout all of time? So a very, very small question, easy to answer. And we also wanted to know, what are their relationships to the geological, geochemical, and biological processes that formed them? So as you can imagine, this project took a really long time, and I really have to credit Bob Hazen and his incredible saint-like patience for going through all of these papers and pulling out all of the modes of formation for the nearly 5,700 mineral species that are approved by the International Mineralogical Association. So we were able to identify approximately 57 different modes of formation and arrange them more or less chronologically from the formation of our solar system into the Anthropocene that we're in now. We were able to identify almost 11,000 combinations of minerals and these mineralizing environments. We call them paragenetic modes. And we made a really huge database. So if you're interested in having this, this is available on American Men, or you can email me and I'll send you this as a spreadsheet. You can also find this on rough.info/IMA. This is the IMA list of approved mineral species, and you can see right at the bottom we have paragenetic mode tags, so you can access all of that information there. It's also, I think we also have it up on MinDat now as well. I think Jolyon has incorporated that on MinDat, so you can find that information there. We're spreading it out. So we have this big data set, and how do I like to visualize big data sets? What makes sense in my brain? That, of course, is a network. For the sake of time, I am not going to go through and explain exactly what we're seeing here. I do have these. These are interactive. If anyone wants to sit down and go through them, I'd be happy to do that. I can send you the HTMLs. But basically what you're seeing here is a graphical representation of the relationship between all known mineral species and their formational environments through deep time in our solar system. So this is kind of all of mineralogy, if you will. I will explain just a little bit. The brown nodes represent mineral species, so there are 5,656 of them. And the colored nodes represent paragenetic modes, or those formational environments. So you can see the mineral, these are the, let's see if this works, these are the minerals here. So you can see all of these minerals form only in this one paragenetic mode or formational environment. There are 57 different paragenetic modes. We grouped them into 11 different colors, just so that you could, just because if not, 57 is a lot of different colors, right? So we kind of grouped them into, are they high temperature alteration minerals? Are they, primary igneous minerals and things like that? So you can see there's a lot going on here. There's a lot to explore and understand. But I'm just going to hit on some of the key findings. And those key findings relate to water, the diversity of the modes of formation, the role of rare elements in mineralization on Earth, and biology, of course. I mentioned that several times. So the first one is water, which you can just look at this network and immediately tell that it plays an incredible role in mineralization on our planet, right? I mean, it is hitting almost every point of that network. So what we found is that 80% of known mineral species form through processes that were driven by water. So the vast majority of the minerals that we have on Earth would not exist without some process or directly interacting with water. We also have paragenetic diversity, or the diversity of the modes of formation. So I mentioned earlier that LNRE distribution. Most mineral species are rare and only a few are common. What that also translates to is most minerals only form in one or two ways. Right? So we can see that 59% of minerals form with only one known mode of formation. And you can see those very clearly because they kind of bloom out like these little mushrooms. They're only connecting to just that one paragenetic mode node. And then 24% of minerals form with only two known modes of formation. So that's the majority of minerals. There are some very notable examples, things like calcite, for instance, but pyrite wins. We've published 21 reported known modes of formation. I actually realized in another investigation recently that it's actually 22, so we just need to publish that as well. But you can see that pyrite, not only does pyrite form in 22 different ways, which is quite a lot, it also kind of spans the network. And what that is telling us is that it forms in very different ways, right? Pyrite can form in these very high temperature systems. Pyrite can form in sedimentary, very low temperature systems. And there are a lot of people who think that there might be biomediation associated with the precipitation of some sedimentary pyrite. So pyrite is a very notable example. It's also very beautiful. So, any excuse to put up some beautiful pyrite pictures. Next, we have the role of rare elements in mineral diversity. So we found in doing this survey that 40% of minerals required one or more rare elements. And these 42 rare elements they're things like literally the rare earth elements, the platinum group elements, arsenic, so on. And they are a very, very, very small portion of the total crustal atoms. They are less than 1 in 10,000 crustal atoms, and yet they play a very outsized role in mineral diversity. And basically what we're seeing here is there are certain deposits like agpaitic rocks, which is what we're looking at here, high temperature alteration systems that concentrate very rare elements. Biology also can do that, which is what we're seeing up here, and I'll show you a little bit more about that in just a second. There are several processes on Earth that are driving this kind of funky chemical environments. And so what happens is if you get a concentration of rare elements, you can actually form mineral species. So we're seeing high concentrations of rare elements equals rare minerals. So I promised you the biosphere. So here we are seeing minerals that are associated with life, whether they are mediated by life or they rose exclusively through biotic processes. They are shown here. It's very interesting that there are a lot of modes of formation that are associated with biology, but they're all really kind of close together. That's telling us something about the way biological mineralization happens on a planet. And that is something that we are very actively investigating right now. But immediately I can look at that and say, okay, something's interesting here. And we also found in surveying this that 50% of minerals on Earth are mediated by life through one way or another, and approximately 34% of those form exclusively through biotic processes, which was a lot. It was more than I expected. So the other component of the evolutionary system of mineralogy is kind of moving again into that predictive space. So what I just showed you was largely descriptive. I mean, we're starting to recognize some trends. We're starting to learn some things about the environments that we're trying to characterize. But this is where we really come into a more predictive space. So I've been able to characterize all the mineralizing environments on Earth and through our solar system. But what if I have a sample? What if my rover on Mars, and this has happened, tells us that we have a sample of pyrite? How do I know how that pyrite formed? It can form in 22 different ways. So which was it? And really the important question in thinking about planetary missions is was life involved in that formation process? And pyrite isn't the only mineral we want to ask this about, but it's certainly one of the important ones. So pyrite is one of the examples that we have really started with, and we have wonderful colleagues who have given us a fantastic database on over 6,000 pyrite geochemical and textural analyses. So this is coming from Ross Large at the University of Tasmania and Dan Gregory from the University of Toronto. And we have been able to do a cluster analysis, so we're calling this natural kind clustering, using various clustering methods, and you can see those clustering results projected here onto a PCA plot. And with that, we have been able to distinguish the modes of formation of pyrite. The preliminary, the start basically, really distinguishes between high temperature and low temperature pyrite very quickly. So we can very easily make that distinction based on geochemistry, and we are now working further to be able to parse out each one of those, and the high temperature and the low temperature cluster, to be able to understand more about which environments each one of these samples may come from more specifically. So I'm really looking to answer the question, when we return those samples back from the Perseverance rover or from future missions to Mars, how did those minerals form, and was life involved? And this method will enable us to answer that question. So we're doing this in a lot of other systems, not just planetary related ones, but I also care about Earth as well. So we have put together several databases you can see here that are just really awesome, and we've had wonderful students be involved in this collection, and they're actually getting to publish papers and learn all about these mineral systems, which has been a very fun part of the work that I get to do. So we have a database on garnet analyses, and that data paper is about to come out right now in ESSD, and it's over 100,000 analyses, and these are very well curated, cleaned. I mean, you can take them and put them in whatever algorithm you want, basically right now. We have put out a paper on looking at pre-solar silicon carbide grains, feldspar, chlorite, spinel. I'm also really excited about some work we're doing on ungrouped chondrites and trying to figure out why they're ungrouped. Several people were talking about chondrites as being, very primitive materials, and there are a lot of mysteries that they hold about the formation and origin of our solar system. So we are trying to use some of these techniques to answer some of those questions. Okay. So I showed a lot of projects, and now I'd like to do a pop quiz, see if anyone can tell me what they all were. No, I'm kidding. I'll go through them just to do a nice summary of everything that I've just told you, of the key findings from this work, the things that I think are the coolest and most important. The first is that a planet's evolution is recorded in its mineralogy. We've been able to predict the number of missing mineral species on Earth. We have observed higher dimensional trends embedded in network topologies. We have estimated complex major and minor chemistry for minerals on Mars, and we can do this for other planets. We've essentially created an instrument that is like sending a microprobe into space. We predicted new locations of mineral deposits and environments, and we've characterized all mineralizing environments in our solar system, and we've quantified the role of water, life, and rare elements within those systems, and we have predicted the formational conditions of minerals based on geochemistry. So basically, my kind of conclusion is that mineralogical frameworks allow us a lens to study these very complex Earth and planetary systems integrated with other fields like biology. And I think that data science and so much of the work that I have been seeing being presented here in this conference, and the methods that you guys are developing, which are so cool, enable this kind of work. So it's been very fun to get to be amongst a bunch of math nerds like myself. I love it. I really enjoyed it. So again, I will leave you with, I think the future of mineralogical and data science and Earth and planetary science is data-driven and predictive, interdisciplinary and integrated, and multidimensional and complex. So with that, I would like to thank my many, many collaborators, who I was not able to mention the vast majority of them today, and my funders. And as Andrei mentioned earlier, I am making a little change. So I am actively recruiting I'm starting next year at Rutgers University, and I'm actively recruiting graduate students, postdocs, and a faculty level data science lecturer, essentially, to help me do some of the work that I'm doing. So if any of you are interested, please seek me out. And, the website's right there. And you can also find me at my website there. And I have a distinctive name, so you can also just Google my name and email me if you're interested. So with that, I think hopefully we have some time for questions.
What a wonderful talk, Dr. Morrison. Congratulations again. Yeah, we do have time for questions. Thank you. Yeah, give him the microphone.
Thanks for this nice talk. I have two questions. The first one is, when you assume life, do you assume carbon life? Do you assume that water is needed for life? I mean, maybe I have more imagination, but I could imagine life with not working with something else and do complete other process and stuff. My second one is maybe more technical going on. You say that when you send the device on Mars, you use basically a proxy to the measure with trained with machine learning. And if in Mars it exists something that we don't have on Earth and therefore you didn't train on, how would you detect it? I suppose the neural net will always give you something.
I love that. There were so many good questions in that. Thank you. So the first question is huge, which asking me that it's huge. We know carbon-based life, right? We have exactly one example of life, and it is what we have here. So what I'm working to do really is to understand what is the signature of life that we see imprinted on this planet. What does an abiotic Earth look like, right? So we have these two kind of very different models. And perhaps when you see a deviation from an abiotic planet that doesn't quite look like this carbon-based life, perhaps then you can know, okay, we have something else. Certainly there could be something else, I mean, why not? I think your imagination is, I guess in like physics is the limit, but certainly there could be something else. And yes, water has been something that historically NASA had kind of the attitude of follow the water. And I think in recent years that has really started to change. And I really don't hear many people saying that anymore, because to our knowledge, you need water for life. To our knowledge, you need water for geologic processes. And geologic processes, geologic cycling is another critical component of having a habitable planet. You need things that are creating energy gradients that life can utilize. So we think not only does life itself probably need water, but geologic processes like plate tectonics and hydrothermal systems and things like that that create these niches that microbes can utilize are also required. So life as we know it requires water for several reasons. But certainly, yeah, I mean, the sky is the limit, right? Like it could, who knows? I don't know. That's beyond my level of understanding. The other question is, yes, so yes, it is a proxy for composition, but only barely. So within a mineral crystal structure, a crystal structure is made up of atoms, and the distance between atoms is related to the atoms themselves, right? So basically, if you put a larger atom in a crystal structure, the crystal structure becomes larger. If you put a smaller, it becomes smaller. So we're essentially mapping out that crystal chemical relationship. So it is a proxy, but it's very close. So we're looking at the changes in unit cell parameters as you change which cations you have in the sites. So that's how we're doing that. And the other component of that question, remind me just of the last. Oh, yes. Okay, also a great question. So we think we actually have found something, a mineral that is not on Earth. So with X-ray diffraction, you are able to measure the structure, right? You're able to see what is the unit cell of this mineral. So when we find something that doesn't coincide with anything that we know to have occurred on Earth, then we could characterize the unit cell parameters of that. What we could not do very easily, we can make some estimates, is determine the composition. Because the way I determine the composition here is by characterizing the crystal chemical relationships that we have measured on natural and synthesized material on Earth. So I wouldn't be able to do that for something new, but we certainly could characterize that we have a new mineral on Mars. And I think, but we're like working on that right now, because I think we have found something that is new. So, you didn't hear that. This is only online until the 15th, so it's fine. Thank you. Those were really, really good questions.
Great. Any other questions? Okay.
Thank you for your very interesting talk. I wonder, from a practical point of view, you use the mineral composition, and I work in compositional data analysis, and you showed two pictures of natural clustering or natural kind clustering. Mm-hmm. And one of them was the second one by Borisovich, I think, used two different ratios on a log scale, which is okay from a compositional point of view, from a methodological point of view. But the other one I did not recognize exactly if you were using raw data or not. My question would be then, what do you think about using compositionally compliant methods that respect the relative scale of compositional data in all the projects where you use the composition of minerals?
So what we do in any of these systems is we work with a geochemist who has a very good understanding of how to normalize these data and how to treat these data, because we recognize that a lot of compositional data requires different normalization techniques. And so basically we work with individuals who have a better understanding than I do as a mineralogist and a crystallographer. So, hearing that you work in compositional data, and I understand there was a workshop at the beginning of this meeting that I really wanted to attend and wasn't able to make it work with the flights, because I would really like to learn more and have more knowledge myself about how to handle these systems. But the way we do that right now is in the same way that I work with a lot of data scientists, I also work with a lot of geochemists. So, thank you.
Is it working? Yeah. I really like your little story about the pyrite sample that you find on Mars, and then you are wondering, is it produced through life or not? But you also said in your analysis that there is a lot of mineral on Earth that need life or the biosphere in order to be produced. So first question is, can you consider these minerals as biomarkers? And then should you maybe actually change your approach to Mars and just think, okay, let's try to scan a lot of minerals until we find one of these, and then we are maybe not sure, but at least fairly confident that life must have been there in order to create them.
Yes, absolutely. So it certainly is something that we are looking for. We do have a list of minerals that are associated with life, and absolutely, if we were to find any one of those, that's okay. Hey, we got it. Of course, if you were to find that, you would have to really do a lot of work to make sure that, as far as we know, it doesn't form through any non-bio pathways, right? But that's something that we keep in mind. Unfortunately, a lot of the biominerals on Earth are associated with higher level life processes. So on Mars, we would really be limited to microbial life, right? It's pretty clear that they never had, multicellular life. They certainly never had animals. So the minerals that form as a result of, bat guano on a mine fire, for instance, I don't think you're going to find that on Mars, right? So those we just know are not going to happen. Although if we did, that would be really interesting. I did get an email once from someone telling me that they swore one of the images we brought down from Mars was a crab. So maybe one day. But yes, so we are actively looking for these minerals. Another issue is kind of coming back to the rarity of a lot of mineral species. So you would need a certain level of abundance to actually be able to detect it. So with powder X-ray diffraction, even in a laboratory instrument, you need a certain amount of any mineral in a powdered sample to be able to detect that. Our detection limit with Chemin is between 1% and 3%, depending upon the mineral structure. So we would essentially need at least 1% of the total volume of sample, which is a small volume of sample. It's like the size of a baby aspirin. I mean, it's a very small amount, but we would need at least 1% of that sample to be that mineral in order to be able to detect it. So we have several things kind of working against us, but it's certainly something that we keep in mind. And any time we do find a mineral that has any sort of biological possibility, we try to, make note of that in the papers. But you do have to be really careful. There have been times in the past when individuals have claimed that, they found things and that didn't go so well. So we do have to be, I forget what the phrase is, but you have to be very careful when you're making these massive claims. But we certainly try to keep that in mind. Yeah. Thank you. That's a great question. These are such great questions. Also, I want to thank all of you because you were so engaged and so nodding along with me and stuff. It's so nice after all of these years of giving virtual talks to be here with you, and everyone's giving me so much, I mean, a couple of you were asleep. I saw that, but that's fine. It's fine.
Good. I think we have another question. Yeah, this may be the last question.
Oh, okay, that will be a simple, naive question. I'm totally ignorant in this field, but I've heard that some other good solvents could replace water to create life. Something with ammonia, something else. Have you used this information that comes from other specialists? Have you used that information in your queries?
That is a great suggestion. And yes, there are people out there who hypothesize other solvents. And I do work with several astrobiologists who are kind of thinking about all of the realms of possibility. We have not made it there in our work yet. We're still, it's still pretty complex to just characterize the signs of life on this planet. So we're not quite to that step yet, but I hope, maybe talk to me in like maybe 10 years or something, and maybe I can generate some models for what that might look like. It sounds like there's a lot of interest in that, so maybe I should be heading in that direction. But yeah, I think that's a really cool problem, and I think that there are people who are thinking about that in a way that we could potentially incorporate that into our work in the future. So I think that's a really cool, I'm going to write that down. It's a good new direction. Thank you.
Can I ask a very short question?
Okay.
What is that one mineral that is not connected to anything else?
Oh, I don't remember right now. I think that might be one of the lunar minerals, and somehow I forget why it got disconnected from the network, but I used to know the answer to that, and now I forgot. But maybe Anirudh remembers. He made these networks. These are his networks. But yeah, it's a lunar mineral, and it's only found in the moon, and so that I think that environment isn't connected with the network. So yeah, good question.